So for capillaries, we have three kinds. We have continuous, then we have what are called fenestrated, and then we have sinusoids. Okay, continuous capillaries, most capillaries. So throughout your body, there's a lot of continuous capillaries. Now, does anyone know what the word fenestra means? What a fenestra is? In Italian, la finestra, mispronounced, is fenestra is a window. So it's probably from Latin. Fenestrated means windows. So windowed capillaries, a fenestra is a window. And then finally, sinusoids are special. So fenestrated capillaries, you'll find these. Okay, well, let's just say capillaries in general are leaky. They're always leaky, except in your brain. In your brain, it's different. So in general, capillaries are going to leak fluid, blood plasma. So the blood, but not the cells that are in the blood, white blood cells, platelets, and red blood cells. So continuous going to be going out to your muscles all over the place. Fenestrated are much leakier because they have windows, gaps in the endothelial layer, the way the cells join. Well, actually, they have pores. So the fenestrated have pores. You're going to find these type of capillaries are going to be in your spleen, in your kidneys, in your small intestine. So places where a lot of things need to get in and out of your blood fast. Finally, sinusoids are only located in a couple special places. Actually, I may have outright screwed up. I hope not. Liver and bone marrow. Specifically, red bone marrow. Sinusoids are these capillaries that not only do they have little windows in them for material to get in and out quickly, they have holes just ripped in them in between the junctions where the squamous epithelial cells interlock. Usually there's actually big rips, or they're not rips, they're just big holes. And sinusoids have openings in them large enough for a red blood cell to get through. So these are the three types of capillaries. So let's look at what they look like. Okay, so let's look at continuous capillaries first. Most common type, most organs. The epithelial cells, the squamous epithelial cells, are joined together with tight junctions and desmosomes, just like they ever are. But what's present in continuous capillaries are intercellular clefts. So in between the cells, the epithelial cells join together. In between, there can be these gaps. Of unjoined memory, of unjoined membrane. So it's going to allow small molecules in and out of the capillaries quick, but they're not big enough for whole blood cells to move through. So here you go. So we're going to see endothelial cell, and you have the typical tight junction, how they're tightly joined, but between some of the cells is an intercellular cleft. So this will allow molecules like glucose to move through, things like that. We have these intercellular clefts, glucose and things like that can get through. That's it. And red blood cells move through, one red blood cell at a time. Capillaries are wide enough for red blood cells to fit through single file. So continuous capillary, most common, skin, muscle. This is the least permeable out of all of them, but they're still leaky. Fenestrated, now we'll see those pores. So the endothelial cells, the epithelial cells joined like they ever are. We still have intercellular clefts, but now we have pores in the actual cells. So where are we going to find this? High rates of exchange. I think I did screw up on this. Yeah, for sure. There's sinusoids in your spleen. That's where I screwed up. Yep. Okay, so fenestrated. You see all these holes? So we have that in addition to intercellular clefts. So large fenestrations, pores, increase permeability. So in your kidneys, small intestines, active absorption or filtration. Finally, sinusoids. They're fenestrated, but the intercellular clefts are ripped wide open to allow a whole red blood cell to fit through. Wide leaky capillaries. So on your notes, you better erase where I put spleen for fenestrated. When I just wrote on the board, I screwed up and put spleen as fenestrated. It's not. Sinusoids are in your spleen. You have the splenic sinusoids. You also have sinusoids in your liver, and in your red bone marrow, there's sinusoids. So make sure you delete that mistake I just made. Okay, so here we go. Here's what a sinusoid looks like. The intercellular cleft is blown wide open. They have an incomplete basement membrane and typically fenestrated. Special locations, your liver, your bone marrow, and your spleen. The reason you have this is because your red bone marrow, what happens in your red bone marrow? What gets made there? Recall you had red bone marrow and yellow bone marrow. Yellow bone marrow would be in the diaphyses of long bones, but in the proximal epiphysis of your humerus femur is red bone marrow. You'd have red bone marrow in flat bones, sternum, your pelvis. What is produced in red bone marrow? Blood. Yeah, specifically the cells of your blood. It's called your hematopoietic system. Hematopoiesis is basically making blood cells. Leukocytes, which are white blood cells, and erythrocytes, red blood cells, are all made in your red bone marrow from stem cells. In order for them to get in your blood, you have the sinusoids are in your red bone marrow. So as the cells are made, they squeeze in your blood through these giant intercellular clefts and sinusoids. Now your spleen filters your blood like your kidneys, but not the same way. Your kidneys adjust water concentration in your blood. Your kidneys adjust what nutrients are in your blood. Your kidneys adjust electrolyte levels in your blood. And your kidneys get rid of nitrogenous waste in urine. So your kidneys filter your body to get rid of certain things and clean your blood. The spleen filters your blood for pathogens So your immune system's in the spleen, some of it. And your spleen is an immune system organ. The spleen also recycles worn out red blood cells. So they're broken down there. So your spleen has members of the immune system in it. So there's sinusoids in your spleen for things to leak out, cells and such. Your liver, same kind of thing happening. Your liver, we'll talk about your liver later. Okay, so these are sinusoids, the most leaky capillaries of all. You can see there's incomplete basement membrane. They have giant tears almost, the large intercellular cleft, and they can be fenestrated. Okay. Fenestrated capillaries, they still have the intercellular clefts, but now they have fenestrations in addition. So you're going to find this where there's a lot of filtration, absorption happening. Your small intestine, absorbing nutrients, kidneys, filtration. Continuous capillaries, the least permeable, but they're still leaky as all get out. They have intercellular clefts. So in your skin muscle. So these are the three types of capillaries, and that's it. Do you have any questions on the capillaries? Capillary permeability, vary. Okay, here's some ways that things get in and out of your capillaries to your tissues. 4 routes in and out. 1, direct diffusion. Diffusion is the movement of molecules, substance from high to low concentration. That's how diffusion works. Like a dye getting dropped in water, it spreads out. That's diffusion. Tear gas being thrown in a room, the gas is going to exit the canister because of diffusion. So diffusion's one way. The way diffusion works is not everything can move through cells. Oxygen, carbon dioxide can, and other molecules. Many can't. Okay, 4 routes in and out. Direct diffusion. Through the intracellular clefts, goodies can move through. Finally, things that can't move through the clefts and can't outright diffuse, maybe they went in through a fenestration, a pore. None of that happens. There's another way things get in and out. Through cytoplasmic vesicles, so endocytosis, exocytosis together. It's also called transcytosis. Objects being actively moved in through the cell's plasma membrane, through the cell's cytoplasm, and out the other side. So these are 4 routes in and out. Direct diffusion, oxygen, CO2, putting nitrous oxide, ethanol, small nonpolar molecules. Through intracellular clefts or windows, the pores, or transcytosis. Now, there are some low permeability capillaries, the blood-brain barrier. You've all heard of the blood-brain barrier. Something crosses your blood-brain barrier. Okay, the capillaries in your brain are special. You don't want any old thing going to your brain. Or maybe you do, but here's the deal. The capillaries in your brain have complete tight junctions. There are no intercellular clefts. Do you think they're going to have fenestrations? There's no intercellular clefts for capillaries in your brain. You think they'll have fenestrations? Hell no. Okay. 0 intercellular clefts. The only thing getting through is that which is wanted getting through to your brain. So highly selective transport mechanisms. So what's going to be the mechanism of choice for things to get into your brain, to the neurons? Transcytosis. So whatever your brain needs, the glial cells, astrocytes are going to be there. They're involved in transcytosis. So actively moving things out of your capillaries to your neurons, like glucose, stuff like that. And of course, glucose is in the cerebral spinal fluid. Highly selective transport mechanisms. Okay, your blood-brain barrier is not a barrier against oxygen or CO2 and some anesthetics because they can freely diffuse. Like a ghost through the wall. Recall the plasma membrane of cells is selectively permeable. It's a traffic cop. But what the plasma membrane cannot stop are small nonpolar molecules like oxygen, CO2, and some other things. I think alcohol crosses it as well. Anything else is blocked. Can't get through except endocytosis, exocytosis, transcytosis. Blood-brain barrier. Let's look at a cross-section of capillaries. The usual deal, normal blood vessels, we're looking at a continuous capillary here. Okay. Poor passage, some substances can get right through the intercellular cleft, and lipid-soluble substances are able to diffuse straight through. So small nonpolar molecules. Blood-brain vessels, nothing gets through. Tight junctions, no intercellular clefts. Additionally, here you see astrocytes wrapped around the capillary. So glial brain cells support the barrier. The only way things are getting out of your capillaries is carrier-mediated transport, transcytosis. However, lipid-soluble substances, fat-soluble, small nonpolar molecules can diffuse like a ghost through a wall. So that's your blood-brain barrier. Questions on this? Okay. Oh yeah, here's astrocytes, okay. Wrapped around neurons and capillaries at the same time. So microglial cells are present too. They're not really forming the blood-brain barrier. Those are just immune cells. Capillary beds. Let's look at this. So you have these capillary beds. We know we're going arteries, arterioles, capillary bed or capillary network back to venule vein. So capillary beds, where there's a lot of capillaries, this is where they're leaky and everything's getting out to your tissues. What's a capillary bed? Network of capillaries running through tissues. Okay. Here's the deal. Precapillary sphincters, though, can shut off blood flow to tissues. So arterioles vasoconstrict, vasodilate, but also there's these capillary beds and these sphincters can shut off, alter blood flow through the capillary network. Okay. In general, as far as your tissues go, who's getting blood? Tendons and ligaments are poorly vascularized. We already know that. Dense connective tissue sucks. Slow to heal. Dense regular, that is. Epithelia is always avascular, always relies on diffusion. And cartilage is avascular. Cartilage will not heal if it tears. So these two need nutrients from nearby connective tissues. So let's look at a capillary bed. Okay, we have a terminal arteriole, and then we have this big central, it's not big, this central vessel here coming off the terminal arteriole is called the metarteriole. Then we have a thoroughfare channel from the metarteriole, and we have a post-capillary venule. So we have terminal arteriole moving into the capillary bed, post-capillary venule, and a central, very small structure called the metarteriole moves through the bed. Off here, we have the true capillaries of the capillary network on either side of the metarteriole. So there's these sphincters, little precapillary sphincters blocking blood flow into the capillary network. So when the sphincters are open, the blood flows throughout the network. Now when these sphincters contract, blood moves just through the metarteriole, and that's it. So blood right through the metarteriole, the thoroughfare channel, and bypasses the true capillaries. So capillary beds can be shut down or they can be open for business. Precapillary sphincters. Any questions on this? Closed for business? Open for business? Okay. Let's look at venous vessels in general. Conduct blood from capillaries toward the heart. In general, blood pressure is low in veins. As blood moves into smaller and smaller arterioles and finally through the capillary bed, you're going to lose a lot of blood pressure. The blood's all going to pull back together, but it's not going to be moving with the force it was before. Okay. All right, we know venules are the smallest veins, and smallest venules are called postcapillary venules, right after the capillary bed. Venules join to form veins. Okay, so I've already thrown a lot of this at you. You already know this. Structural differences. Lumens are larger in veins. Tunica externa is thicker than an artery, less elastin in veins, and the walls are thinner. The overall, for the tunica externa, media, and intima together, all three tunics, a vein is thinner than an artery. But a large proportion of veins, tunica externa. 65% of your blood is in your veins at any time. The blood is slow to return back to the heart. Okay, so here's a play-by-play, just a summary, just comparing elastic artery, muscular artery, arteriole capillary, relative tissue makeup, thicknesses, and then looking at venules and veins. Okay, so here's how blood gets back to your heart. So we know the heart's a muscular double pump. Blood is forcibly being ejected through conducting arteries. Bam, pulsatile. It slows down big time because of capillary beds, gets blocked. Comes back slow meandering Mississippi River, moving real slow. So how do we gonna deal with this low venous pressure and get blood back to the heart? Valves, that's why there's valves and veins. So you have valves in the veins, it prevents backflow of blood. Where are you gonna find valves? In your limbs. Not located in veins of your thoracic and abdominal cavity. So your trunk, no valves. Only in your limbs and then in some of the veins of your neck. Another way that blood gets back to your heart is something called the skeletal muscle pump. Skeletal muscle squeezes the veins and milks them. Milks them and gets the blood back. It also will squeeze the valves. So your skeletal muscle squeezes, the veins get squeezed by muscle contractions, which returns the blood. Now, there's something else. So you have valves are in your limbs, but there are no valves in your thoracic and abdominal cavity. And there's also valves in neck. how do you think blood's gonna get back to your heart when it's in the abdominal region and thoracic region? How's it getting back? What mechanism could make it kind of move along? If there's no valves, like what's to kind of prevent backflow and get it going? And in your limbs, you have muscles, so they're squeezing the blood along, and they're also closing the valves. You have what's called the thoracic pump, the thoracoabdominal pump, intra-abdominal pressure. Basically, breathing and your diaphragm moving around and your abs doing their thing, there's pressure differences that happen in your abdominal cavity and in your thoracic cavity. So that's how the blood gets back. Call like your thoracic pump. Heard it called that, thoracoabdominal pump maybe, but thoracic pump. So intra-abdominal, intrathoracic pressure returns blood in those regions. Valves are in your limbs. Okay, skeletal muscle pump presses against the thin-walled veins. Here we go. Skeletal muscle pump and valves together. Direction of blood, okay? The blood's moving through. When skeletal muscle contracts, it squeezes the blood up through the valve, but the valve behind that region that's contracted ends up closing as blood pulls back against it. So it's to help with a one-way flow of the blood. Squeeze it, puts backflow pressure, the valve closes. Blood's just moving up or back to the heart. Any questions on that? The skeletal muscle pump and valves. Okay, blood in your abdominal region, maybe going out, I don't know, blood's returning from your intestines or something like that. That's not a good example. Blood returning from somewhere in your abdominal cavity. How's that getting back?
Valves.
No.
Pump.
Huh?
The skeletal muscle pump.
No. Toby, how does it get back? Toby. Mr. Toby. Rainy. Okay, we're gonna pick on Megan.
Oh yeah, go on.
Okay, wait. Okay, Rainy, what? How does it get back?
What?
Blood returning from the abdominal cavity. How is that facilitated?
Returning from the abdominal cavity.
Yeah, from veins in the abdominal region.
Okay.
What mechanism aids in that?
You mean how does it flow to the heart and then to get oxygen again?
Okay, that's okay. Never mind. Okay, let's pick on Megan. All right, Megan.
Is it the thoracic abdominal pressure?
Yeah, that's it. Perfect. Bam.
I was getting there.
I know you were. I know. I know. Boom. All right. Let's look at it real quick. Let's just take a look at this for a gosh darn second. Let's get the official term because I'm getting senile. As my beard gets gray, I grow increasingly dim. My memory fades.
A lot of my demented residents say that too.
What's that? Oh yeah. Thoracic pump theory. Oh, let's not do that. The thoracic pump. Okay. Let's leave out the thoraco-abdominal pump because I'm thinking about the thoracolumbar fascia still. Okay, the thoracic pump. The negative pressure in the chest during inspiration that pulls venous blood into the vena cava. Bam. Beautiful. Thoracic pump. That's short and sweet and straight to the point. So let's do it. Changes in thoracic abdominal pressure, thoracic pump. I don't know why your book doesn't talk about the thoracic pump, but way back when, in 2002, when I had to take evolution and diversity of the animals, we were traumatized with physiology in bloody detail all semester long. And the thoracic pump was definitely part of it. I don't know why they would only talk about the skeletal pump here in the valves without talking about the thoracic pump. How are you going to talk about there's no valves in the veins of the thoracic and abdominal cavity and not say why? Thoracic pump is in effect. Let's look at something else. Let's not look at that at all. Okay, let's get out of there. Okay, so that's how blood's getting back. Now, what do you think is going to help blood get back better from your limbs? Can you think of something that would aid in venous return? Besides, we have this skeletal muscle pump and venous valves. What can you say about your limbs that would help blood return better?
Would be vasoconstriction.
No. What about your limbs? Would you probably want them doing? What do you want your
And
limbs?
we want them moving.
Yeah, moving.
As you move, the blood moves.
Exactly, that's it. What if you're standing still, perfectly still, for like 8 hours a day? It's not good. How about people
You
that
probably
have
have
to,
a lot of problems.
yeah, you have to stand there behind a register, not moving. Yeah, it's not going to be great. And there's other things too. You could end up with like edema, swelling, because the lymphatic system works kind of like your veins do to get fluid back. Your lymphatic system sucks up all the fluid that the capillaries lost. So it's good to be moving. Okay. All right. We have something called an anastomosis, which is singular. Anastomosis. Sounds like some old historical novel with anastomosis. Anastomoses is plural. Singular. What is this terrible word, vascular anastomosis? Basically, these are where vessels converge so that there's multiple pathways. So the arteries on your heart have anastomoses. This way, you have to have like a coronary artery has to be like 90% occluded before you'll actually get a myocardial infarction. Basically, it's like this. You're driving down the street, the freeway, and there's multiple other freeways to get to the same place. Now, when you're driving down the 15 and there's a traffic jam, it's blocked, you're pretty much screwed, depending on where you're going. There's only one way to get to San Diego in the end. There's not a whole lot of back streets. Whereas maybe you're driving somewhere else and the freeway is backed up, you take a different freeway. So that's what these anastomoses are. In general, arteries, veins, and anastomosize much more than arteries do. However, in your heart, there's you have anastomoses with respect to arteries. You want to see an example of anastomosis or anastomoses? Hold out your hand and just squeeze or whatever and look at all the veins on the back of your hand. Those are venous anastomoses. So blood can return more than one way. So in anastomosis, vessels interconnect to form vascular anastomoses. Organs are going to receive blood from more than one arterial source. You have this going on with your brain, and you have this going on with your heart. Two places where blood really counts. So neighboring arteries form arterial anastomoses. So you have collateral channels for blood to get to where it needs to go. Places where you don't have this is like at the ends of long bones, places where like if blood supply is cut off, considerable damage results. So veins anastomose more frequently than arteries. Okay, here's a venous one on your heart, but it's going to happen with arteries on your heart too. Vascular anastomoses. There it is. Okay. For some organs, though, this isn't happening. So when blood supply is cut off, considerable damage. Any questions on anastomoses? No? Okay. Okay, so we're ready to talk about circulation. We'll just look at a few and then we'll look at full-on systemic to your limbs, like the names of the arteries and then the veins. So how is blood going to move out your right arm, down your fingertips, and return back to your heart? So we'll look at that kind of stuff on Tuesday. But we'll look at pulmonary circulation right now. Okay, pulmonary trunk exits the right ventricle, splits into right and left pulmonary arteries. What do you think would happen next after the pulmonary arteries? Pulmonary what?
Veins.
Not quite. Pulmonary arteries, yes, you're thinking for the heart. Because what I've given you so far is the pulmonary circuit. But let's think about this. Pulmonary trunk, right and left pulmonary arteries, into pulmonary arterioles, to pulmonary capillary beds, are going to return in pulmonary venules, finally the pulmonary veins. Right and left superior and inferior pulmonary veins, into the left atrium. Okay, left and right superior and inferior pulmonary veins carry oxygenated blood in the left atrium. So for your lungs, you have the pulmonary circuit is sending blood out to pick up oxygen. However, the lungs themselves, the tissues of your lungs need a blood supply. So blood is also sent to your lungs a different way. Blood is sent to your lungs from the systemic circuit to provide your lungs with nutrients. The pulmonary circuit is only sending blood to pick up oxygen. If we're looking at a model of the lungs, like when we get to the respiratory system, if we were actually physically in class, we'd have the model and you'd be able to see the difference between the two. Most likely I'll be able to pull something up virtually and we can look at it. Not today, later. Okay. Vessels of the pulmonary circuit, thinner walls than systemic vessels. Maximum arterial pressure is lower in the pulmonary circuit. Because it didn't have far to go, and you don't want high pressure being sent to blow out the capillaries in your lungs. There it is, pulmonary circulation. Okay. Deoxygenated blue, pulmonary trunk, out the left and right pulmonary arteries. Okay. We're going to move into pulmonary arterioles, which are going to be blue, deoxygenated, and to pulmonary capillary beds. Pulmonary capillary beds are wrapped around all these air sacs in your lungs. And right there is where gas exchange happens. Carbon dioxide out, oxygen in. Then they're going to converge into precapillary venules, pulmonary venules, finally into the pulmonary veins, which are going to be red. Left superior, left inferior pulmonary veins. Right superior, right inferior pulmonary veins. So that's it, pulmonary circuit. Off the systemic circuit, there's going to be blood brought to the lungs, and there it's going to be the usual pattern, red for arterial blood supply going to lung tissues, blue for venous. But for the pulmonary circuit, everything's reversed. Okay, so the aorta. The aorta exits the left ventricle. It's an artery. What kind of artery is the aorta? Your choice is conducting, or is it distributing? Or is it elastic, or is it muscular? What kind of artery is the aorta?
Elastic.
Yes, which is also known as a conducting. Okay. Heck of a lot of elastin. Okay, so that's the aorta. Largest artery in the body. Oxygenated blood away from the heart, high pressure. Well, the aorta has some different parts. It has the ascending aorta. It's where the aorta is coming up. Then it has the aortic arch, and then the descending aorta. Finally, with the abdominal aorta. So the ascending aorta comes up out of the left ventricle. We'll see what that looks like. The aortic arch, okay, it's posterior to the manubrium. It has three main branches that come off the aortic arch. 1, 2, and 3. One is called the brachiocephalic trunk. Then we have left common carotid and the left subclavian. We'll look at that in a second. Like now. Okay, so here you see, here's a pulmonary trunk rising up out of the right ventricle. And then out of the left ventricle, you have the aorta coming up. So where it's rising up is the ascending aorta. And then the aorta arches and sinks back down behind the heart and heads on through the diaphragm. So this is ascending aorta right here. Then we have aortic arch right here. And then we have the descending aorta, consisting of the thoracic aorta. When it's going down, once it penetrates the diaphragm, switches its name to abdominal aorta. Here we go. Ascending aorta, aortic arch, descending aorta or thoracic, abdominal aorta, and then the aorta is going to branch off in your pelvic region into the common iliac arteries, left and right. Okay, so what's going to happen is arteries are going to split off the aorta all over the place. For your lower limbs, the aorta splits up into the right and left common iliac arteries. And then those are going to branch up. The common iliac arteries are right away going to split into the internal and external iliac arteries, and all pandemonium ensues. Okay. Well, let's look at some goodies that are coming off the ascending aorta. The ascending aorta, nothing comes out of it other than two arteries. The very first arteries to leave the aorta, they are right and left. The very first arteries to leave the aorta come out of the ascending aorta. They consist of a right and a left. Name those arteries. The very first two to branch out of the aorta comes out of the ascending aorta. Right and left coronary arteries. Right and left coronary arteries come straight out of the ascending aorta. First thing the heart's going to do is supply itself with some blood. Not that it has a mind of its own, because it doesn't, but that's just the way it works. Then we're going to have three branches. So out of the ascending aorta, there is nothing coming off other than the right and left coronary arteries. The aortic arch, we're going to have the, this one is called the brachiocephalic trunk. The next thing to come off is the left common carotid artery. It's going to split into internal and external carotids, but that's later. The third thing to branch on off the ascending aorta is the left subclavian artery. Your subclavian arteries go to your upper limbs. Okay, so this brachiocephalic trunk, all this is a common artery that's going to split right away into the right common carotid and what else would you guess it splits into? One other thing. What do you see on the left here? Left common carotid and left subclavian. The brachiocephalic splits into the right common carotid and the right subclavian. All this brachiocephalic trunk is like a fusion of those carotid and subclavian for the right side, and then it splits. Some people, this is different, and this is the usual pattern for most people. Okay. All right, descending aorta continues from the aortic arch. Thoracic aorta, T5 to T12. Abdominal aorta ends at L4. And then we're going to have to split into the right and left common iliac arteries. So there, you see, ascending aorta. What are the two arteries that immediately leave the ascending aorta? There's only two that come out of the ascending aorta. What are they? Griselda, Morelia. Which two arteries leave the ascending aorta? Griselda.
I think she said her audio doesn't work.
Oh,
Yeah. But the right and left coronary artery.
that's it.
Okay.
Okay. Okay. Cool. So what's the next thing to come off of the, well, we're going to go to the aortic arch. What's the first thing to branch off the aortic arch? The first artery to branch off the aortic arch.
The brachiocephalic trunk.
Exactly. What's the next branch?
Left common carotid.
And what's next? What's the third thing to branch off the aortic arch?
The subclavian.
Yes,
Mhm.
left subclavian, yep. So the brachiocephalic, you see how it splits into the right common carotid and the right subclavian? So it's just a fusion of those two. And some people, there's weird things where the left subclavion's attached to the brachiocephalic trunk, and everyone's unique, but this is the usual pattern. Okay, so the subclavians head on over to your limbs, and there's some important things that split off of them. The carotids, well, we know where they're going. Okay, so at the bottom, abdominal aorta ends at L4, divides in the right and left common iliac arteries, and then we're going to split into internal and external iliac arteries, right and left. So the thing with, when we talk about on Tuesday systemic circulation, the way blood vessels work is they're like streets. You're driving down the street, it has its name, then it takes a turn and changed its name, which is irritating, but they do that all the time, right? When you're driving around, streets bend and change their name. That's exactly how blood vessels are. So when we head through the axillary region, your armpit, we're going to start talking about axillary arteries. When we head on down your brachium, we're going to talk about a brachial artery. When we go into your forearm, radial and ulnar arteries. There's a tibial artery. There's a femoral artery. Things are making sense. Well, heck, here's everything. That is a very small picture. Okay, so here's the subclavian artery. As it heads on down through your armpit, the axillary region, it's the axillary artery. As it heads on through your brachium, it's the brachial artery. Okay, it's going to split. The street just wide out. We had a street and it's split into two smaller streets. Okay, we have the radial artery and the ulnar artery. Then we head in your hand and there's some things. The deep palmar arch, the superficial palmar arch, digital arteries. Okay. So let's look at your head and trunk. The common carotid arteries always split into an internal carotid artery and an external carotid artery. The internal carotid artery passes through a very special hole in your temporal bone. Name that opening in your temporal bone that the internal carotid artery heads on through. What, the hypoglossal canal? Name that opening in your temporal bone that the internal carotid artery heads on up to your brain. Okay, Ashley Rhodes, you tell me. Name the opening that the internal carotid artery passes through.
Carotid canal.
Boom, there it is. You thought I was trying to trick you, huh? Nope. Okay. So the common carotid arteries branch off into external and internal carotid artery. Internal carotid artery is going to service your brain. Head knob up through the carotid canal. The external carotid artery just branches off into a bunch of arteries for your face, your skin, things like that. Now, there is an artery that splits off the subclavian artery. Right after, well, those carotid arteries are coming off. Right after the carotid artery and the subclavians kind of part ways for the brachiocephalic trunk, or if we're talking just the subclavian to the left side, we have the vertebral artery. It's one of the very first ones. The vertebral artery heads on up through the transverse foramina of the cervical vertebrae and heads on through the foramen magnum, I'm pretty sure, I'm hoping, and goes to the back part of your brain. So the carotid arteries are going to temporal lobes, frontal lobe, vertebral arteries head on up through your foramen magnum. They travel through the transverse foramina and then head through the foramen magnum. Cool. Okay, let's go down to your left and right common iliac arteries. They're going to split into internal and external iliac arteries. External iliac arteries going to branch off. We have a major branch is the femoral artery heading through your thigh. It's then going to pass through the popliteal region, the back of your knee, and it's going to change its name to popliteal artery. And then that popliteal artery is going to split. We're going to have an anterior and posterior tibial artery. Anterior tibial artery is going to move through the interosseous membrane between the tibia and the fibula. There it is. So that's the whole thing. So let's see what's going on in your head. Here we go. Common carotid artery. Okay. It's going to split, and we're going to have the internal carotid artery go through the carotid canal of the temporal bone. There it is. The external carotid artery, do not need to know all this. All you need to know is that the common carotid artery splits into the external carotid artery and the internal. The internal goes through the carotid canal to service your brain. The external has all these branches to all different parts of your head, not to do with your brain. Okay, so the internal, yeah, there's an ophthalmic artery, but whatever. Okay. Now let's see. Here we're coming off the subclavian. Right here, we have the vertebral artery splitting off the subclavian. And there we go, vertebral artery moving through the transverse foramina. Heads on up. And actually your vertebral arteries are going to be paired on either side through the transverse foramina. Then they're going to fuse into something called the basilar artery, move up through the foramen magnum. Okay, let's not look at all this yet. We'll come back to this. Okay, now let's look at the brain real quick. Actually, let's save it for Tuesday to look at the brain. Okay, your vertebral arteries supply posterior brain. They join to form the basilar artery. Here we go. Here's the subclavian. First branch, vertebral arteries through transverse foramina. Head on through the foramen magnum and join is the basilar artery. Okay, we'll look at the circle of Willis on Tuesday. This is a massive anastomosis for your brain. So here's these vertebral arteries. Join is the basilar artery. And then we had the internal carotid arteries came up through the carotid canal. We basically have thoroughfares, multiple ways for blood to get around your brain, just in case one route's blocked off. We'll look at this on Tuesday. The cerebral arterial circuit, known as the circle of what you talking about, Willis. Okay. Okay, there's a guy for you. All right, so here's one thing I want to talk about real quick. I'm flying all over the place, and we're going to just look at all this on Tuesday. We looked at the aorta today, aortic ascending aorta, aortic arch, thoracic aorta, abdominal aorta, splits into right and left common iliac arteries. We looked at the vertebral artery, heading up through transverse foramina, heading through the foramen magnum. Let's just look at a couple things that are coming off of the abdominal aorta, because this is going to put these collateral sympathetic ganglia into context. Now you're going to know why we have the celiac ganglion for the sympathetic, why we have a superior mesenteric ganglion and inferior mesenteric ganglion. The hypogastric, let's not worry about that. Abdominal aorta, as it penetrates through the diaphragm, we have this structure called the celiac trunk. The celiac trunk that comes off the abdominal aorta has some important arteries coming off of it over to the spleen, the splenic artery, the gastric artery, and hepatic artery. So it's the celiac trunk is going to split into an artery going your spleen, your liver, and your stomach. Why it's called the celiac trunk, I don't know. It just is. So we're going to take their word for it. What's sitting on the abdominal aorta right next to the celiac trunk? The celiac ganglion, a prevertebral sympathetic ganglion. It is named that because it is right here. So the collateral ganglia for the sympathetic, they are in front of the aorta. Another one we had for the sympathetic was the superior mesenteric ganglion. Why? Because it's above the superior mesenteric artery. Superior mesenteric artery is supplying blood to your small intestine. Finally, there's an inferior mesenteric artery coming off of the abdominal aorta. Now you know why these sympathetic ganglia have the names they do. You also have the celiac plexus, which is where parasympathetic and sympathetic neurons are running through. So those are those collateral ganglia. They are on the abdominal aorta, superior to these arteries. That's why they have those names. So the celiac trunk, the superior mesenteric artery, the inferior mesenteric artery. Okay, here you see those common iliac arteries. There's some other arteries coming off here. They're easy, they're paired. Renal arteries, where are they going? Kidneys. What is there? Right and left. Gonadal arteries, where are those going? Your gonads. Are they paired? Yes. Do you have two gonads? Usually. Right and left, gonadal arteries. Adrenal, suprarenal gland. It's not so straightforward. Middle suprarenal artery. Let's not go there. Cool. Okay, there's our guy again, pressure points. Okay. Vertebral arteries, we looked at those. We'll talk about the circle of what you're talking about, Willis, Tuesday. Okay, so here we go. Celiac artery, celiac trunk. You have the celiac plexus for the sympathetic. That's where the preganglionic and postganglionic neurons synapse. You also have a celiac plexus, parasympathetic fibers passing through it to intramural ganglia. We have a gastric artery, left gastric, we have a splenic, and we have a common hepatic artery. That's all coming off the celiac trunk. Okay. We have the superior mesenteric artery, and it has all these different branches. Middle colic artery, intestinal arteries, right colic, ileocolic artery. Just know there's a superior mesenteric artery. That's it. If we are in class and there's models that showed some of these, it would be worthwhile to look at, but we're not in class and I don't have a model. So let's not go cuckoo about stuff happening in the abdominal cavity. Know that there's a superior mesenteric artery and an inferior mesenteric artery. Right here. Bam. So we're going to have celiac trunk, superior mesenteric artery, inferior mesenteric artery. What are all these divisions? They're just servicing different parts of your intestines. Celiac trunk servicing your stomach, liver, and spleen. Collateral ganglia along the abdominal aorta. Celiac ganglion, superior mesenteric ganglion, inferior mesenteric ganglion. There's a hypogastric down here somewhere, but whatever.